Okay, so unequal cell sizes are bad. Remember last time I talked about two designs. One design you should avoid, one design that you'll probably not run into. The one you should avoid is the hierarchical design. The one you probably won't run into very often is Latin square. It's perfectly acceptable. Here we're going to talk about something that you should just avoid almost as much as you should avoid hierarchical designs. So most designs actually assume equal ends. Okay? Notice how I call it n in all the designs we talked about. Say n equals 5, n equals 4. I'm saying equal number of subjects per group, except for the simplest ones, like a one-way analysis of variance. A one-way between subjects analysis of variance, you can have different numbers of subjects per group. I can also tell you, though, that there's a thing you learn sometimes about weighting means. We used to teach, we don't anymore because everybody's you got a computer. But there was a thing people were taught for a long time that actually turns out is incorrect. Some people modeled the stuff and went, no, it doesn't really work that way. So there was a thing that people used to be taught about weighting means that isn't really the case. So it's beside the point. You can have unequal ends. If you go to the thesis conference next week on Friday, which I encourage you all to do to support your fellow students and see what many of you will be going through next year. That's next Friday.
What time is it?
I think it's at 1 or 1:30. Or it's one of those, it's in the afternoon.
I'm very concerned.
It's done by 4, because that's when the bar opens. And we go drinking. So, probably 1 or 1:30. Yeah, I'll find out. There'll also be a thing in the Algoma you know that email you get every morning that you delete as soon as it arrives?
Yeah.
Oh, wait. The way that you know it's 8 o'clock in the morning? Oh, the Algoma you know is here. Delete. No one has anyone ever said, oh boy, the university newsletter email's here? Never. No one. But you'll see one of my students that does a simple one-way analysis of variance on her data. And she's got unequal cell sizes. No problem with a one-way ANOVA. No problem at all.
Is it in the speak?
Oh, the drinking is. The talks themselves are NW200. Yeah, if you're just interested in the drinking. Yeah.
No, the talk is where?
The talks are in NW200. The one that everybody calls the fishbowl.
Okay. Let's see there.
Yeah. It's there. You'll see some really cool science. It's really neat. So let's say you have unequal ends if you have anything more complicated than a one-way ANOVA. What then? What to do? What is to be done? Which is the name of a political pamphlet written by Vladimir Lenin. I don't know why I know certain things. I just do. Maybe we can estimate the missing values. And in fact, if you look on SPSS, you can tell it to estimate missing values. People say use the mean. Sometimes people say use the median. Depends on what people you're talking about. You might want to use the mean if you've got data where you don't have a lot of variance, where the variances are similar in each group, which they really should be. If you've got a few high numbers or a few low numbers that would pull the variance in that one cell, because we're talking about a cell not having enough data. If you're going to put that, it's going to pull it up or pull it down, you might want to use the median instead. Okay? Because you know the median isn't affected by extreme values. Right? It's one of these cases you should always know what average somebody's talking about. If they're talking about the median or the mean. Right? The next thing you might want to ask yourself is, instead let's do this. Why don't we look back to our model? Let's say it's a 2x2. X equals mu plus alpha plus beta plus epsilon. Maybe we could say, we know what the grand mean is. We can just calculate what the A effect is, what the B effect is, and what alpha beta is, and go from there. That's a possibility. The thing is, sometimes you might think to yourself, well, I don't want to include the interaction, just like in our quiz example, we didn't include beta effects on them. Because we don't expect there to be an interaction. So we would think that theoretically the data should turn out like this or that. So you include interactions. That's a question you can ask. It's not like I'm not saying this is a way to cheat. I'm saying that you might think to yourself, I don't want to include the interaction because there shouldn't be one. That's got to just be statistical noise. You're making all kinds of extra little assumptions here, as you can see. No matter what, you've lost degrees of freedom, or because you've arbitrarily assigned a value, right? As soon as, let's say we've got 5 numbers here, 5 numbers here, 5 numbers here, and 3 numbers here, the bottom, let's see, your version bottom left, we got to estimate 2 values. If we're going to do that, we're fixing 2 more values. So I guess I shouldn't say we're losing degrees of freedom. We aren't gaining any by adding those numbers. They're still fixed. No, they're still fixed, right? Because if I just arbitrarily assign them, they aren't free to vary. Okay. So you see the logic of this so far? Using logic exceedingly loosely here. I wouldn't do this. Now there are other ways to deal with it. We could estimate values. We can also use calculations that I'm not going to get into how to do them because you let computers do them. Or you know how to do matrix algebra pretty well. So I use computers because I'm really lousy with matrix algebra. Most of the analyses I've talked about in this course, when I've shown you the sums of squares, I've shown you what are called type 1 sums of squares. This should tell you there are other types, if there's a type 1. So they're fine if ends are equal. They work at that. They're actually built for ends being equal. The reason the expected values work out the way they're supposed to, so we know what to divide by what, are because the ends are supposed to be equal. It's one of those. They don't work as well when ends are unequal. They work, but just not as well as they should. They tend to make mistakes. How do we know they make mistakes? People do what are called Monte Carlo experiments. They do these simulations, and they include missing values, but they actually know what the real effects are in the population. You generate a population of millions of numbers, and then you randomly select some numbers, but you miss some values. So you actually know what's happened because you've designed the population, and then you see if it detects the things it's supposed to detect. This is the fun of reading the Journal of the American Statistical Association. And I am putting fun in the air quotes out there. But there are, of course, type 2 sums of squares. Aha! So it's all matrix algebra. They're good when there's missing values. They can deal with it nicely. And you might think, well, great, why don't we just do type 2 sums of squares all the time? If there's an interaction, they don't work properly. So they're great if there's no interaction. They were perfect. They were intended for situations where you had, say, 2 main effects or 3 main effects or whatever, but you had no interactions. So you're probably thinking to yourself, you're saying to yourself, I bet there's something called type 3 sums of squares that deal with interactions. And there are. You probably don't know if there's an interaction or not, because if you knew it, you probably wouldn't do the experiment. You probably don't know. So if there's no interaction, type 2's fine. If there is interaction, type 3s are what you do. So you use type 3s. Type 3s, again, this is done with matrix algebra. And in fact, when SPSS, if you take a look at the outputs that you guys generated from the last assignment, you'll note that they actually would have said type, where are we here? Anyway, if you use the SPSS to do it, it said type 3 sums of squares as the header. Because by default, SPSS and any other statistical program worth anything will give you type 3 sums of squares. Because type 3 sums of squares are equal to type 1 sums of squares when the number of subjects is equal. So we learned the type 1 analysis because I don't want to teach you matrix algebra because I have to reteach it to myself. And also, no. You can just do that some other time in your life, okay? And then you too can get half out of 15 on a quiz in your first year PhD. Because you guessed 7, that was the right answer. to a great big multiplying two matrices together. I don't know how the hell it's going to happen. I told you guys about that. I just guessed 7 because I was told by a math prof in first year calculus. Guess 7 once in your life, you're bound to be great. Yeah, it worked once. It's my one time it worked. It's never going to work again. So instead, we teach you, and also it's easier to explain the type 1s. This is a variation from this mean, so the type 1s make more sense that way, theoretical, or sort of intuitively. But our software always uses type 3s. In fact, if n's are equal, type 1's equal, type 2's equal, type 3's. If the n's are equal. That's great. Type 2s are mostly for regression. So they'll come back. You have to not calculate it, but you will hear about them again. So this isn't a huge deal. The thing is, a lot of people, what they do when they do post hoc tests is they don't realize that post hoc tests want equal ends. They don't want unequal ends. So they'll use unequal ends and they're using type 3 central squares and they go, oh, fine. Who cares? But then they go to a Tukey or a Stigma Cools or something, and it requires equal ends. Right? So, go ahead.
Why would you not have equal ends?
Geez, I can give you a reason right now that Maria, my student, doesn't have equal ends because people didn't show up for the experiment. She's doing an honors thesis.
Oh, so something like
So they're like unforeseen
out of
reasons?
control, yeah.
Almost always. Animals die.
Oh, okay, no.
Things like that happen, right? I mean, science...
Nobody really does it on purpose.
It's
Pretty rarely, yeah. If someone did it on purpose and they were working for me or with me, I'd say, go collect more data, please. But that doesn't happen when people work with me because I say, make sure you have 15 subjects per group or whatever the heck
That's
it's
what
going to
I'm
be.
saying. You would make it the same.
Yeah, you would never plan it. I can't think of a reason you would plan it that way.
So it's out of your control usually.
Yeah, usually. Now, it might be a case where you say, okay, I can see that the placebo group and the sham lesion group are not different. So I'm going to put them together into one group, and it'll be twice the size of the other group. People do that.
Okay.
I would rather they didn't.
Measurements within those would still be the same.
Oh, they're fine. Yeah, sure. But I wouldn't do that. I would just say, why are you doing that? That would be the thing I'd ask people. Because I've seen that before. I don't like it. I mean, I just, and it's not just the sort of part of me that's like everything should always be nicely balanced. It's because math, I mean, it just works better with equal ends. For the post hocs, if you're doing regular analysis, it doesn't really matter.
Yeah, but if you're designing your experiment.
Maybe you don't design with unequal ends, then you're out of your mind.
Okay.
You don't know how to do, you probably didn't do well in 2127 or 3286 then. Those are research methods courses for people on the internet. We're listening, not for people on the internet. And I'm looking at the microphone like it's the internet and I'm talking to it. Hello, internet.
You hear that, internet?
Yes. Do you hear that, internet? Now, what you might do, in fact, what I usually say to students when they have these problems, now Maria doesn't have the problem of, well, she can't collect any more data. So I said, do you have time to just equal these out? And she said, not really. I said, okay, I don't care. It should work. I mean, if there's an effect, we did a power analysis before we did the experiment, and I said, we need this many subjects per group. One of them has that minimum number. If we don't have an effect, I don't care. Then it's not there. Not a huge deal. Though there's something there. There's something. I'll say, though, that this chair is just in the wrong place. That's the first thing I said. It's got to be somewhere. So, yeah, what I would typically say is just go collect more data. Right? So you need more people in group 3. Go get some people, test them in group 3, and then we add your data for fun. Now you can't just. This is different than something called p-hacking. P-hacking is when you say, oh, I'm at p is less than 0.07. I'm just going to keep testing people until I hit 0.05 and stop. That's cheating. Look, if it's at 0.07. You should look and go, that means there's a 93% chance this didn't happen because of sampling error. Oh, didn't you imagine 0.05? I don't care. It all went in exactly the direction I expect is what happened for me. Versus at 0.056. And I said, it's fine. It worked. If someone says it didn't work, they're wrong. It went exactly the way you expected it to go, just that you said, well, what about collecting more subjects? I said, no one who works with me will p-hack. I will not allow it. No. People will do that. My favorite case of this I heard of, I didn't see this myself, but a buddy of mine, my buddy Todd, I've told you about Todd before, he was our TA when I was in grad school. He was collecting data, he was reading a paper, he was reviewing a paper, and then they said, we didn't get a significant correlation. So what we did is, but it was going in the direction we expected, so we simulated 20 more numbers. See, and then they just said, oh, those are degrees of freedom too, and now it works. You can't do that. That's not even p-hacking. That's not even wrong. It's not that it's not right. It's just not even wrong. It's in a whole different world. That's not how anything works in the universe. You don't just make things up. Right? It's like when you were a kid and you said, maybe you flipped a coin, or you do rock, paper, scissors, and you go, okay, you do the first one, you do the paper, covers rock, and your friend goes, okay, no, 2 out of 3. No, 3 to 5. 4 to 7. Keeps going until eventually he wins and goes, yeah, 5 out of the left, 5 out of the 9, I win. That's just cheating. P-hacking's close to that, but not quite. Just making up numbers and saying, oh, we'll just make up some numbers, that's just cheating. Of course there's a type 4 sum of squares. Why wouldn't there be? There's no type 5 for ANOVA. But there is a type, notice I was even a V for 5. Pretty good, right? I took Latin. I know Roman numerals. Whoa, type 4s work with empty cells. That's cool. See, empty cells are when you have like A1, A2, B1, B2, and then you have data here, data here, data here, and nothing here. Like literally no data. So it works like this. That would be an empty cell situation. Pretend these are cell mates, 4, 2, and 2. What would you put here? What do you think? I'll see if you can give me a reason to. So what would you put as the empty cell here for A2, B2? What would you put as the empty cell here?
4.
Okay. Why 4?
Because it would become a pattern.
It looks nice and it's symmetrical. Sure. That's good. This is good. That's a good reason. What's another one?
That's a good answer.
What's another number you can put there?
0.
Why not? Why 0, Jay?
Well, going between A1 and A2, it will go down by 2.
There you go. There you go. So you're both making. So you're thinking interaction. You're thinking main effects. Sure. What about 3 million? There's no argument against that either. That's the problem. I don't know what goes here. Type 4 sums of squares are really fun to do because they're bizarre. Mathematically, they come up with a solution. They solve a regression model, basically. So, or fit a regression model. But they make a guess as to what number should go there. And the number depends on if it does the A effect first or the B effect first or interaction first.
So would this be the same circumstances before? Like you didn't get
Here what you do.
complete data?
Yeah, the thing is here you have no data. Yeah.
Well, why would you have a blank cell is what I'm saying.
Because you don't know how to design experiments. No, seriously, that's what it is. It's because you don't know how to design experiments.
So you made a mistake.
You made a mistake.
And you can't go back and fix it, so you do this.
And this has happened before. I talked the other day about how one of the ways you can make money as a psych grad student, a little bit of money on the side, is be a statistical consultant. And I did this. And people from a lab, I won't say anything else about it because I don't want to disparage them. And they do good work too. They're not academics per se, but not an industry either. So it's an organization. Did this work? And they had a stats program, and they called the guy who wrote the stats program, who was my stats prof in grad school. And he said, you should go upstairs, knock on door number 307, and his name's Dave Broadbeck. He's a really good student. He's one of my TAs for graduate stats. Ask him and pay him. So the guy showed up, and he introduced himself and said, it's nice to meet you, blah, blah, blah. What do you need? And he said, I need you to come in, help me analyze my data with this program called PowerStat, which we're using, which is still a great program that doesn't exist anymore. And I said, okay, that'll be at least $200, and that's for 1 hour, and it's $2 an hour. He said, okay. I said, Okay, because it's 1992, and I'm like, that's money. So I go down to their lab, which is in the same building. I look at his tutorial design. I go, you can't do this. Because they were like, it wasn't just a 2x2. You know how I analyze this, by the way? I turned it into a one-way ANOVA, just do 3 groups. I can do that. I can't talk about interactions anymore, but I can say groups are different. But he had like a 3x5 and like 2 empty cells. And I said, I can't analyze these data. I said, are you really interested in the 2 things come together? Like how they interact? He said, yes, can't be done. I said, I can give you an answer, but I said, but I can give you an infinite number of answers, all of which are correct. Or all of which are incorrect. He said, I don't understand. I said, well, yes, I can see that. Because I was like, a pretentious jerk. I'm 26 and I'm smarter than the old guy. So, but I mean, they wrote me the check. And I said, the best thing to do is go back, get more money, and run those 2 cells. If you can do that, I can come back down here and do it for you in 10 minutes. And again, there'll be $200 more. And I don't know if they did it or not. I think maybe the guy was pissed off about that because he never got me back down there. But I got $200. You can't analyze empty cells. The only way you do this, like I said, turn that into a one-way ANOVA with three levels. No more interaction, but at least I can find out. At least all is not lost. At least all is not lost. Questions about this?